The laws of thermodynamics, and you've read about them, we've experienced them, and we've used them implicitly, at least the first law we've used implicitly, throughout a lot of our work here, especially with this bottle engine. The first law says that when we add thermal energy to a system, it has two possible effects. And it can have both of these effects, but that the thermal energy added is split up between the two. One is it can increase the internal energy of the system. And of course, that means you increase the temperature of the system. Okay, so we can put energy into a system and increase its temperature, and we can also do work. Now, when we added thermal energy to the bottle engine at constant volume, there was no work done because nothing was expanding. So all the delta Q went into change in internal kinetic energy and raised the temperature of the system. When we then allowed the gas to expand, we continued increasing the internal energy of the system. The temperature kept going up, but we also did work. And we had to add enough energy, thermal energy, to accomplish both of these tasks. So we change the internal energy, and or we can do work, and we can split, depending on the system, the delta Q can be split between these two results. Okay, so again, delta Q is the net thermal energy in, delta U is the change in internal kinetic energy, and delta W is the work done by the system. Now, the second law of thermodynamics, which the example that we just looked at addresses, says that we can't convert all of our delta Q to work. There are limits. Okay, as we saw with the bottle engine, we had to put delta Q in to raise the temperature. Then some of our delta Q went into work. If we then allowed the system to expand adiabatically, we wouldn't be putting any more delta Q in. We'd get the work out of the system. We'd get the work as the area under the curve, the closed cycle, and then we could calculate the efficiency. If we allowed the system to expand isothermally, we would have to continue to pump energy into the system so that the gas wouldn't cool off as we expand it. And in that case, there'd be even more delta Q into the system. In any case, whatever delta Q we put into the system, it can't all go into work. And that there's a limiting efficiency. Efficiency being defined as the delta W, the work done by the system, the area under the curve, in other words, divided by the delta Q that goes into the system, the thermal energy we put into the system. And that cannot be greater than TH minus TC over TH, where TH is the temperature of the hot reservoir. In the case of the bottle engine, that would be the temperature of the hot water. TC, the temperature of the room as we used it, over TH. Now this tells you that the greater the difference between TH and TC, the more possible efficiency you get. With the bottle engine, we could cool the engine down, or the bottle down, with ice water and use hot water. So we'd go maybe from 0 to 80 Celsius. We'd have a lot higher potential efficiency, and we would notice that we have a lot higher efficiency. Now, one thing that we can say about the bottle engine is we don't approach this possible efficiency. We don't get anywhere near it. Usually our efficiency is measured as a fraction of a percent. Okay, the TH minus TC for, let's say, 360 minus 300 Celsius is 60. We divide that into the 360, we get 1/6, or about 16%, whereas we only get a percent or a fraction of a percent out of the actual bottle engine. That's because the cycle we use in the bottle engine is not optimally efficient, not even theoretically. We can get a theoretical maximum for that engine, and it's nowhere near 16%. There's one engine that does achieve that theoretical efficiency, not practical efficiency, because the engine isn't even very practical, but it's called a Carnot engine, where instead of an isobaric, isochoric addition of energy, constant volume, then an isobaric, constant pressure, then maybe an adiabatic, and then again a constant pressure cooling like we used with the bottle engine. The adiabatic, the Carnot engine will use an isothermal process, then an adiabatic, then another isothermal, and another adiabatic to go through its cycle. And I think I just named those exactly the wrong way, but we won't worry about that. You can read about that. A Carnot engine can theoretically achieve this, but no higher efficiency. And that's the best you can do. That's the second law of thermodynamics in one version.